So we shall consider this example. Okay, so it's a truss given, right? So these at these location, these members are not connected. Uh, Not connected. Okay, so this is element 1, 2, 3, 4, and 5 and 6. Okay, you have 1, 2, 3, 4 nodes, right? So together you have a reaction at here, let's say R1, and reaction at here, let's say reaction here and reaction here, right? Always define it on the global x and y direction, right? Okay, so this has a force of 10 kilonewtons, 5 kilonewtons, and the other nodes are okay. Length is given. For these members, length varies, right? So it's 1.4 root 2 meters, right? So you have to define. So you have 6 elements. So you know what is the element stiffness matrix, right? That is going to be AE over L into C. Remember C squared, CS squared, blah blah blah, something matrix. You have to determine that, right? So for the first element, there are 6 elements: 4, 5, 6, right? You have to determine whether. So I'll call this first node, second node, third, and fourth. So angle is which it makes with the positive x direction. So I can take first element going from first node to second, not from second node to first node, because then its x direction is like this. So this will be your angle. It's not that like that. Okay. So always go from x positive direction is this. So this is 90. First node to second node, the element is defined. First to second. Second one is second to third. Second node to third. Second node to third node. This is node, right? The which I am circling the node. Third one is again not from 3 to 4. Then it is not according to our configuration, but it's from 4 to 3. It's then 90. 4 to 3. 4 to 3. Okay. So the fourth element from 1 to 4, not from 4 to 1. Okay. If 4 to 1, it is the angle is 180. If 1 to 4, that's 0. This is fifth element 1 to 3. Angle is then 45. The sixth element is 4 to 2, not from 2 to 4, 4 to 2. Then 4 to 2 means this is the angle. Defined from 4 to 2. The angle it makes is 90. Second one is 0. Third one is 90. Fourth one is 0. This is 45. This is 135. So this is theta. Now you can determine the solve matrix and A. So for first 4 element, L is 1 meters. Other things not going to change. For these two, L is 1.41 meters. Right? AEN does not going to change. AEN same. Right? So we can use an Excel spreadsheet to calculate these values and assemble it, right? So I will go with so we have sheets here. Right, let me zoom it. Right. So your A and E given. A is this one. E is this is Newton meters. Okay. Yeah. Yes, Newton meters, I think. So L is 1, L2 is 1.5 meters. This is meter to the power 2. This is, I don't remember exact. So whatever it happens. So for the first, so there are 4 angles actually. 0, 40, 45, 19. So I calculated the sine values and cosine values, because in Excel you have to convert it to radian and then calculate cost, call the sine function or cos function. Okay, you have to make the angles radian and then call it. Then default comes with the radian angle. So this will be the portion you have to calculate, right? So I will calculate it like this. So now my AEI over L1 is this, right? I have calculated AEI over L2 is this. These two are not going to change. This is for element 1, 2, 3, 4. This is for 5 and 6. So I can calculate it. This is cos squared, right? For element 1 and 3, this 2 and 4. This is for 5 and 6, right? So this is cos squared theta 1. Theta 1 is 90, right? So for element, this is for element 1 and 3, it is 90, right? Element 2 and 4, it is 0. Element 5, it is 45. And element 6, it is 6, right? Right. For element 1, you have to consider only these 4, right? So cos squared theta, cos theta sin theta, cos theta sin theta, sin squared theta, right? This half is the entire minus thing of this one, and as well as this one, and this is exactly same as this, so you can easily calculate those things, right? And that's same for element 1 and 3, and for element 2 and 4 likewise you can calculate this same thing. Cos theta sin theta are there, and element 5 you can calculate this. Still I haven't multiplied by AEIOL. So once I go down with that, so I will multiply each element by this value, right? AEIO 1, right? So everything has been calculated here, and this is my element stiffness matrix, and I have put this one into the matrix, right? So that nothing outside the matrix, so that I can add and subtract anything directly, right? So I have calculated this is for element 2, and so this is for element 5, and it's AE over L2, and same as for element 6, right? So I will call these things to here, right? Element stiffness matrix. Now I have it, right? Now I need to, so this is the exactly a bar element which is angled and placed in the spatial coordinate system. and we define with respect to the global displacement, right? So you have already like this. Just remove the color for now. So this is your matrix. So this is how to assemble it, right? So to assemble, you have U1, V1, U2, V2, U3, V3, and U4, V4, U1, V2. So everything is there. This red color is for just to notate the rows and columns, and here are the global displacements, right? So this is U1, V1. Okay. U4, V4, right? So that's, so when you multiply the global stiffness matrix with the displacements, so this is K into U is equal to global nodal forces, right? This is the actual matrix. So I will explain you how to determine this. For now, our objective is to determine this matrix. So for instance, U1 element, right? So that's going to be so that comes with like that I explained earlier, right? So in the fourth video, you have to assemble it, right? So let me show you for one moment. So you have the global system U2, V2, U3, V3, U1, V1, U2, V2, like that. So you need to determine, let's say, this element. So it's U1, right? So at first node, you have connected element 1 and 3, right? So element 1, U1, V1, U2, V2, U1, V1, U2, V2. Element 1, element 2, it's going to be U2, sorry, element, it is 3 to 2, right? U3, V3, U2, V2. I don't remember that. No. It's 1 to 2, okay. 2 to 3, right? 2 to 3. U2, V2, U3, V3. So there are several elements connected at one. So I'll call that elements only for now. So element 5 is 1 to 3, 1 to 3, element 5, 1 to 3, that means U1, V1, u5 v5, sorry, u3 v5, 1 to 3, u3 v3, right? u3 v3, not 5. Element 1 is connected from 1 to 3 node, right? u1 v1, u3 v3, u1 v1, u3 v3. That element is okay. Then you have 1 to 4, the fourth element, right? Those are the connected at node 1. 1 to 4 means u1 v1, u4 v4, u1 v1, u4 v4. So you need u1 row, u1 column. Okay, that is also important. u1 row, u1 column, right? u1 row, u1 column. Here no u1 here, so no contribution from this member stiffness matrix. So there's a contribution from this u1, u1. This element comes. This element. Now remember, AEIOL is with inside the matrix. I have multiplied everything by that. Okay, don't keep it outside. Right? Multiply it because we need to simplify that. Right? These three should be added together. That's it, right? For instance, if you consider this one and v3, so you should consider u2 row v3 column. Okay, u2 row v3 column. So if there's another matrix, you have to consider that. So here v3 column is there, but u2 row is not there. u2 row should be there and v3 should be the column exactly as it is, right? So likewise, you can add those things and make this matrix, right? Once you make this matrix, you know u1 v1 is there, u2 v2 is there, likewise. And but you actually know u1, so the first node and third node are the pin support, right? So that the displacements are 0, right? Displacements are 0. Sorry, the fourth node, right? So that you will have some reaction forces, like I explained. Let's say R1, this is R2, this is R3 direction, and this is R4 in Y direction, right? And at second node, you don't have, so you have member forces are cancelling each other because the joint is connected, right? So I explained it in the previous video. So the remaining thing is only no load in x direction, but you have 10 kilonewtons. So that means sorry, not 10 kilonewtons. Is it 10 kilonewtons? So okay, I'll just consider it's 100 kilonewtons and 50, yeah, 10 kilonewtons. Okay, 10 kilonewtons and 5 kilonewtons. So that means 5,000 newtons and 10,000 newtons, right? And from the third node, you don't have any. Show that. From the first node, you only have these two reactions, R1 and R2. Right, at this node you don't have x forces in x direction, but you have in minus y direction. That's why minus 10,000, right? This is in x direction, that is plus 5,000. This is in x y direction 0, and this is R3 and R4. Always x comes first and y comes second, right? At a node R4, right? And another thing, the displacement at these two locations are 0 because it's a pin support, and there will be a displacement in these locations, right? So that I have made the displacement are 0 at first and fourth node, but there will be reaction force R1, R2. Okay, there will be displacement at second and third node. So how to solve this is you have to close these things, right? So I'll just this one. It's confusing. So whatever the displacements are 0, you can cancel that rows and column. U1 is 0, so that means you need to cancel that row and U1 column. V1 is 0, so that means you have to cancel that row and cancel that column. U4 is 0. V4 is 0. You have to close that row and close that column, right? So that you will be remaining with these things, right? This is the reduced force matrix. This is the reduced stiffness matrix as it is, and these are the displacement, right? These are the unknown displacement. So that if you multiply this force matrix by this stiffness matrix inverse, you will get the displacement. That's what I did. So this is the inverse matrix. So how to get it is also 4 by 4. So I take M inverse this matrix and control shift enter, right? So this is the force matrix, and then you multiply it by, so displacement will be also 4 by 1 matrix. So M mult matrix multiplication this matrix into the second force matrix, right? This will give the displacement in meters, right? And then you can plug it back, these displacements here, you know those, and then you multiply these values and take the forces, right? So these are the forces. Let's see if you multiply this, shall we get this right? So matrix multiplication, so you need to select the exact number of cells to represent the matrix whether you which you need to get as the output, right? So in this case, this is a 8 by 8 matrix into 8 by 1 matrix, so you will get 8 by 1 as the output. So I have selected 8 by 1 and press equal sign, then a mult. So create select the matrix 1, then matrix 2, and control shift enter. So I'm getting exact force like this. So that means my method is fundamentally correct, right? So I have get the nodal displacements. So the reactions 16 newtons. So these are in newtons and kilonewton. So newtons, right? So these are the nodal reactions, right? So now I obtain the reactions. Now I need to consider the member forces, right? For the member forces, what you have to do is, you remember, we did something in the second video. I'll show you. So hope you can see this. So we defined a global stiffness matrix, right? And we assembled it, and we found what we did was we found the unknown displacements first, right? Using the known forces, right? When we plug back to this, and we know this whole matrix, and we now know the whole displacement matrix, and we found the unknown forces, then now it's clear R1, R2, and R3, R4 are there, right? It is actually the P1, P2, right? I have used another notation. Okay. Now we have R1, R2, and R3, R4. That is with U1, V2, right? So we have determined that. And this is R1, R2, 3, R4. We need to determine what we called F1 and F2. This is for a simple case, right? It's F1 and F2, right? So what we need to do is actually, so this is a you don't even need to so this P1, right, and R1 and F1, there's some relationship, but when you determine the nodal displacement, you can see, you can determine directly the axial displacements along the joints, right? W1, W2, if you know U1, V1, because we have already determined this, right? So it's just a matter of plugging into the transformation, right? When you can transform it to axial direction displacements, right? So because W1 is U1 cos theta plus V1 sin theta. W2 is U2 cos theta plus V2 sin theta. What we actually doing is we use matrix to simplify this. It's like a bit standard, right? So when you know W1, W2, since you know this matrix AE over, it is not going to change, and you can find whether it is positive or so the tension or compression, right? So what I'm going to do is, so theta is again here, right? This is for element 1. Okay, so this is these are the local displacement along the longitudinal direction. Okay, U1, U2, element 2, U3, U4, element 5, U5, U5, U dash, U underscore 5, U underscore 6. That's along the longitudinal direction, right? It's like this. You have an element U1 is this, is in the axial direction, and U2 is this, exactly along it. So if it is element 1, U1 is this. Okay, U underscore 1. This is U underscore 2. Okay, if this is true, if the element is even angled, right, then you need to angle these things as well, because this is for 1. Always, whatever the member position, U underscore and U underscore thing is in axial direction at 2 nodes, right? This is always the first node. First one is first node, right? Where the elements was defined first, right? So you remember that is actually this is the W1 in that case, right? W1. Yeah, that's easy for you then. So element 1 is connected for first node and second node. So that means U1, V1 and U2, V2, right? U1, V1 and U2, V2, right? Element 2 is connected for 2 and 3. That means U2, V2 and U3, V3, right? So I'll have I'll show you the picture. Not third node, fourth. So you can see the element 1, this one is connected to first node and second node, right? Okay, that means u1 v1 and u2 v2 is related to that, right? That's okay. For this one, third, second node and third node. Okay. So for element 3, it was defined from fourth node to third node. That order is essential, right? So that means u4 v4 and then u3 v3, element 3, right? Element 3 u4 v4 and u4 v4 u3 v3, right? That order is important. Element 4 from 1 to 4, u1 v1 u4 v4, that's anyway 0, right? Element 5 1 to 3, that's again you see. Element 6 4 to 2, 4 to 2 means u4 v4 u2 v2, u4 v4 u2 v2, right? So once you understand this, this is W matrix and that transformation, then u1 v1, right? So you can determine easily, right? So for transformation matrix is there, sin theta cos theta sin theta cos theta sin theta 0 0 0 0, cos theta sin theta cos theta sin theta cos theta sin theta cos theta sin cos theta sin theta cos theta sin theta for element 5, element 2 and 4, element 1 and 3, right? You just need to multiply. For instance, for element 1 you need to multiply. W1 is a 2 by matrix, 2 by 1 matrix, matrix multiplication. This is the transformation matrix multiplied by nodal displacements of first member in direction, in order, right? First member is connected from 1 to 2. That means u1 v1 u2 v2. You remember sixth one is connected from 4 to 2. Then u4 v4 u2 v2. That order is essential. Okay, here are your displacement. Likewise, you can get the get these displacement on a member. Once you get these, you can easily consider. So you remember this matrix, W1 in W2 equal to AEI over L, and this matrix times, sorry, F1 into F2. So the member force, member tension or compression is equal to like this kind of a form, like F1 F2 was something like this, AE over L, then 1 minus 1, this matrix into W1 and W2. You remember? You need to multiply this matrix by this and then multiply it by AEI over L, then you get the member force, right? For instance, for this is, yes, for this, you have to multiply this matrix M multiply this matrix is the first, multiplied by this matrix. No, it's the first one is order. You should multiply it in order. First thing is this matrix, then it is multiplied by W1, W2, Control Shift N. You have the displacements, right? First matrix is this, then W1, W2, and you have to multiply by corresponding AEI over L, right? AE over L, and then you will be getting the forces. Actually, you can see F1 is similar as F2. F2 is same as, So these are the members at a particular, so member force at two ends, right? So what does this mean actually? Can you see? It's same but changed from the sign, right? Same here, it's zero member, change from the sign, right? So what does this imply? What does this imply? So F1 is 66 and minus 66. So we shall see. So F for member 1, F1 is 66. So you remember we defined member force in the same direction, F1, F2, right? You can see the same direction. Now my F1 is positive, F2 is negative. We can see what kind of force that is. F1 is positive, F2 is negative. Negative means this direction. So which force is this? It's a compression, right? If this force negative, then it's in other direction. If it is negative, this is exactly should be positive, right? So that is a tension, right? So this is telling if it is positive and negative, then it's a compression. It's negative and positive, it's a tension, right? So you can see this is positive and this is a compression, right? This is compression. Sorry, this is tension, right? This member negative and positive, right? This is positive and negative, that's a compression. This is zero member, no member force in that. This is negative and positive, right? So that means it's a tension. This is positive and negative, so that's a compression, right? So these were the displacement I obtained earlier at the nodes, right? This, right? So you can check whether these are actually true, right? So I'll keep this 66, so everything like here, right? I'll go to the SAP, right? So I'll go to the SAP, right? So first thing is I need to, I won't show the modeling. I will show you how to model. I think I have, so no, I will model this first. Is it necessary? Oh, not, right? Or whatever. This is exactly, I have defined these sections, right? So the members, and it's a pin support, right? Right. So height is 1, length is 1 meters. So I have defined the materials as well, right? Because we need to have the exact materials that depends on the results, right? So modify materials, you can see I have given the correct modulus of elasticity in, so 2 to the power 11, right? Remember. And also I have defined the sections as well. FESC 2, define depth is 0, 0, 1, 0, 0, 1, then the area becomes 10 to the power minus 4, right? and the material is met, what I defined earlier. So then material and the cross section area okay, E value and the A value okay, length is in the model, right? So that will calculate the AEI over L, and I have member forces, right? So first thing is this is a truss, so you have to release the members ends, right? So you have to release moment 3 and moment at the end and first node. So it's already released. So at this location you have a load. I call this dead load. So it's this you have 10,000 10 kilonewtons, right? Okay. Here you have 5 kilonewtons in the x direction. It's okay, right? Oh, sorry, it's kilonewtons, right? Newtons there. How can that be possible? My unit is, yes, now it's okay. 10 and 5, right? 10 and 5 there. So I need to set the self weight 0. So I have self dead weight, self weight multiply 0. So that won't calculate the self weight. So our results can be approximated to exact finite element results, right? So now it's okay. I can run the simulation and see. Right. So you can see I have to change the loading into 10,000, right? When I load, so then my displacement will be changed according to that, and I feed it here and calculate the reactions. Reaction found 0.65, 3.35, right? And I feed it here, and I'm getting the member forces as 6.6, 3.4. The displacement will be from here, right? Something around 1433 at node 2, right? So you can go and check whether these are true, right? So you can see 1.63 and 5, 3 and 5. So these are correct, right? Okay. So even you can check the displacements. So you can see 33 and I don't remember the other displacement, right? So the member forces you can check. Axial loads are 6.6 compression, 3.3 tension, 1.6 compression, 4.7 compression, and 2.3 tension, right? So it's exactly as the uh, Excel sheet that we defined, that we did manually finite element analysis. So you can see this is the base of the any of the software, right? So if you know the concept well, you know how it comes, right? That's essential because anybody can model this and get a result, but civil engineer should know what is the concept behind this. Your objective is not to perform this kind of finite element analysis, but to know the concepts, right? If you know the fundamentals well, you will know where did it go. So if your model is wrong, you know, okay, if your results are wrong, probably I know, okay, my results are affected by A, E, L value, right? Probably I might have incorrectly assigned those. So I know that, right? The person who just know how to model will not know that, right? They don't know how the analysis concepts are done, right? So you know that. That's the role of a civil engineer, right? Especially a structural engineer. Thank you very much.